Hey, glad you're here. Maybe it's nighttime where you are. Maybe the world's finally gone, still quiet streets outside, curtains swaying a little in the breeze. Maybe a dim lamp or the low buzz of a fan keeping you company. Wherever you are, however you've arrived, I'm glad you made it. Let's just drift for a while. There's nothing to figure out right now. No rush, no noise, no to-do lists tapping at your shoulder. Just you and me and a calm little corner of the universe to explore together. Out here, the stars don't shout, they whisper. And if you sit quietly enough, if you listen with the soft part of your mind, you can hear what they're saying. Tonight, we're following one of those whispers. It's the story of a star, one that lived big, died loud, and left behind something strange, something spinning, something small and powerful and lonely in the most beautiful way. They call it a pulsar, and in a few minutes, you'll understand why. But before we go too far, you like floating through these quiet little journeys, and you want more calm stories about space and stars and the soft corners of the cosmos, you can tap the like button. It helps more quiet minds find their way here. And if you feel like coming back again, you're always welcome to subscribe. This is a gentle place, and there's always room for one more. Now, let's start from the beginning. It begins, of course, with a star. Not the kind that twinkles in our sky, not even the kind that warms our Earth. This one was bigger, heavier, brighter, so massive, its own gravity was always trying to pull it inward. And so powerful, its fusion core fought back, burning hotter than anything we can imagine. For millions of years, that balance held. Gravity pulling in, fusion pushing out, a perfect cosmic tug-of-war. But nothing lasts forever. The star burned through its fuel, step by step, fusing hydrogen into helium, then helium into carbon, carbon into oxygen, climbing the elemental ladder until it reached something it couldn't burn: iron. And when the fuel ran out, gravity won. The core collapsed in on itself, fast and hard. Protons and electrons smashed together into neutrons. The center shrank to the size of a city, while the outer layers came crashing down. And then, it exploded. A supernova. Not a sound, not a flash, more like a shock. A pulse of light and force and matter thrown across space, lighting up everything in every direction. The star died, but not quietly. What was left behind? That dense little core, the spinning one, the one that didn't crumble or burn away. That's our pulsar. Small, heavy, unbelievably fast, and somehow, still glowing. Let's get closer. Let's go see what it's like, what it feels like to float next to something that used to be a sun, and is now a kind of cosmic heartbeat, ticking away in the dark. We're close now. This pulsar, it's barely the size of a city, maybe 20 kilometers across. You could walk from one edge to the other in a few hours, if you could somehow survive standing on the surface, which you can't. Not even for a second. Because this is not a place like Earth. The gravity here is crushing. If you dropped a paperclip on its surface, it would hit with the energy of an atomic bomb. A spoonful of its matter weighs more than Mount Everest. There's no air, no breeze, no colors really, just a dense, cold crust under you, smoother than anything ever built by human hands, and a magnetic field so strong it would erase every credit card on Earth in an instant. And yet, in the middle of all that strangeness, it pulses. Not in a way you'd see with your eyes. It's not blinking like a flashlight. It's sweeping out invisible beams, radio waves like the spinning lights of a lighthouse. Not every neutron star does this, only some. The ones with just the right tilt, just the right spin, just the right magnetic alignment. Those are the ones we notice, the ones we call pulsars. Right now, if you could close your eyes and feel time the way a telescope does, you'd hear it. Tick, tick, tick. That's the beam passing over Earth as this tiny star spins around dozens, sometimes hundreds of times per second. Some go even faster, over 700 rotations a second. That's like a spinning top whirling in your hand, except this top is heavier than our sun and older than any empire. They don't need fuel to shine. Their energy comes from rotation, from momentum. They are, in a way, engines of pure spin. And over time, they slow down, slowly, gradually, The pulses get further apart, as if the heart of the dead star is getting tired. But it takes millions of years. Some pulsars are young, just freshly born from a supernova, with bright beams and wild spins, chaotic, fast, blazing with radiation. Others are older, worn down, calmer. They spin slower, like an old record player near the end of a song. There's even a kind that's been spun back up like cosmic clockwork. These are called millisecond pulsars. They orbit with a companion, usually another star, and steal some of its material. That falling matter spins them faster, tighter, like rewinding a watch. One of the fastest pulsars we've found spins about 716 times every second. That's faster than a kitchen blender. But this isn't kitchen physics. This is space. And these aren't toys. They're remnants of stellar violence, burning with invisible light. You might be wondering, how do we even know they exist? Well, the first pulsar was discovered in 1967. It showed up on a radio telescope as a perfectly timed pulse, so perfect, in fact, that the scientists at first thought it might be a signal from intelligent life. They nicknamed it LGM-1, Little Green Men. But soon, they found more, and the pattern became clear. These weren't messages, they were beacons, warnings, leftovers from collapsed giants. Today, we've catalogued thousands of them. Some live alone in the darkness, some dance in binary systems, orbiting another neutron star, or even a black hole. A few have planets orbiting them. Imagine that worlds circling a dead star, bathed in radiation and the endless rhythm of a pulse. Even now, astronomers use them like lighthouses, not just to study stars, but to understand time itself. Pulsars are so regular, so consistent, that we use them to build galactic clocks, better than atomic clocks. A pulsar doesn't skip a beat. Its pulse is more steady than anything we've ever made. And in that rhythm, that slow, quiet ticking across space, we've learned to measure things that are otherwise invisible. The bending of space, the shape of gravitational waves, the hidden mass of distant galaxies. It's strange, isn't it, that something so small, so distant, so silent, could become one of the most precise tools in the universe. But that's what happens out here. Big stories in small packages, tiny remnants that carry the weight of stars. And through it all, you and I are just drifting, listening, floating in the space between the pulses. So let's float a little farther out now. We're still near our pulsar, but we're zooming out just enough to see the bigger picture, like stepping back from a painting to notice the whole canvas instead of just one color. Imagine this: a spacecraft far from Earth. So far, the blue of home is just a fading dot. No satellites nearby, no GPS signals, just the deep dark stretching in all directions. And yet, we're not lost. Because on board, there's a kind of map. Not a map of roads or terrain, but a star map made entirely of pulses. The timing, the rhythm, the shape of each signal, all from different pulsars scattered across the galaxy, each one sending out its own beat, its own quiet tick. By listening to those signals, the ship can figure out exactly where it is. Not using a compass, not using radio towers, just the sky itself. This is called X-ray pulsar navigation, and it's real. Just like how ancient sailors used the stars above to find their way across the sea, we're now using pulsars, dead stars, mind you, to sail across space. Because they don't skip beats. They don't forget. They don't change their minds. A pulsar spins and spins and spins, and every time its beam brushes past us, it's like the tick of the most reliable clock you could ever imagine. We even call them cosmic clocks. Some scientists are working on using these pulses to build a galactic timekeeping system, one that doesn't rely on Earth at all. If we ever spread out, if we ever build stations or colonies far away from home, we'll need something better than what we've got now. And the universe, as it turns out, has already built the system. We just had to learn how to listen. And then there's this other thing. A strange thing. A quiet ripple you wouldn't even feel. Not with your skin, not with your ears, but maybe with the deepest parts of space itself. Gravitational waves. They were only confirmed a few years ago, but they've been traveling for billions of years. They come from black holes crashing into each other, from stars collapsing, from the universe breathing in ways we're only beginning to understand. But here's the thing. When one of those waves passes through a region of space, it stretches it, just a little, like tugging on the corners of a rubber sheet. Not enough to hurt, not even enough to notice, unless you're looking for it with something unbelievably precise. And that's where pulsars come in again. See, when a gravitational wave passes between us and a pulsar, it changes the timing, just slightly, like one tick shows up a few nanoseconds early, another, a tiny bit late. By watching lots of pulsars at once, all across the sky, scientists can detect those ripples like watching a field of tall grass sway in the wind and realizing something invisible just passed through. It's beautiful, really. This whole system so quiet, so consistent, letting us hear the slow, deep music of the universe playing in the background, all because some stars died and kept spinning. They don't know they're helping us. They're not trying to be useful. They're just existing, persisting, turning endlessly in the dark. And yet here we are, using them to learn things we never could have dreamed of otherwise. You and I, right now, are floating beside a thing that used to shine like a sun. It collapsed, it shrank, it survived. And now it pulses across space as steady as a heartbeat, as lonely as a single drumbeat echoing in an empty valley. There are thousands of them out there, some spinning wildly, some barely holding on, some alone for millions of years, others caught in the tug of a nearby star. Every one of them a story. Every one of them a leftover flame from a cosmic fire long since burned out. And the universe doesn't erase them. It lets them keep spinning, not as stars anymore, but as something stranger, more extreme, more mysterious. The light from the pulsar we're watching now, it's already been traveling for hundreds, maybe thousands of years. By the time it touches Earth, it's older than the tallest trees, older than electricity, older than memory. And it still arrives exactly on time. We measure it, we listen, we catalogue every tick and hum and whisper, not to control it, not to change it, just to understand. That's all we've ever wanted, really, to understand what's out there. And maybe, in doing that, to understand ourselves a little more too. Now, as we hover near this pulsar's invisible lighthouse beam, you might sense just how different it is from any star you've ever imagined. It's not bright in the usual way. It doesn't glow with soft golden light or twinkle like distant candles. Instead, it radiates in waves. Our eyes can't see radio waves, X-rays, even gamma rays. These beams slice through space, cutting a path that sweeps past us like a cosmic fan spinning tirelessly in the dark. Picture the pulsar's magnetic field, stretching far beyond the star itself, curving and twisting like invisible ribbons. This magnetic field is so strong, it could strip your credit card's information from 1,000 miles away or more. If you tried to stand near it, your body wouldn't hold together for long. But from this distance, we simply marvel at its power. This magnetic energy channels particles-tiny bits of matter that speed away from the pulsar at nearly the speed of light, creating jets and winds that ripple through space. These winds can sculpt surrounding clouds of gas and dust, shaping the birthplace of new stars, or carving glowing nebulae that shine with otherworldly colors. Imagine the pulsar as a cosmic artist, painting with invisible brushes that only the universe can see. And here's something amazing. These pulsars aren't just leftovers, they're storytellers. Each pulse, each flicker, carries a message from the past. Scientists listen carefully, like decoding ancient Morse code sent across unimaginable distances. The timing, the strength, the pattern of these pulses can tell us about the pulsar's age, its speed, its magnetic personality, and even the space between us and the star. Speaking of age, pulsars can be surprisingly old. Some have been spinning for millions, even billions of years. Over that time, they slow down, their pulses growing further apart, their magnetic fields gradually fading. It's like an ancient clock winding down after keeping perfect time for eons. But there are exceptions to every rule. Magnetars, for example, are a special breed of neutron star related to pulsars, but with magnetic fields 1,000 times stronger. If our earlier example felt powerful, imagine something so intense it could rearrange atoms and even warp the very fabric of space nearby. Magnetars sometimes erupt in bursts of X-rays and gamma rays, flashing so brightly they outshine entire galaxies for moments. These eruptions are like stellar tantrums, brief but breathtaking. And while magnetars tend to be quieter than pulsars when not flaring, their occasional outbursts remind us just how wild and unpredictable the cosmos can be. You might feel the faint echo of these flares even here, on Earth, as tiny shifts in our planet's upper atmosphere. Now, circling back to our steady pulsar friend, it's not only a cosmic clock or a lighthouse, it's also a tool that helps us answer some of the universe's biggest questions. By watching pulsars carefully, scientists have confirmed predictions made by Einstein's theory of gravity. Pulsars in binary pairs, orbiting one another in tight, dizzying dances, allow us to observe how gravity warps space and time. When these pairs spiral closer and closer, losing energy in the form of gravitational waves, we see the universe's invisible rhythms made real. And here's a curious thing. Some pulsars help us search for planets. Just like Earth orbits the Sun, some pulsars have their own tiny companions planets that survived the star's death, or formed from the debris afterward. These pulsar planets are unlike anything we know on Earth, exposed to intense radiation and strange environments, yet somehow they endure. There's a certain poetry in that, don't you think? Live at least, worlds persisting in the shadows of dead stars, dancing in the pulse of cosmic light. As we continue, imagine drifting farther still, through the gentle night, through the whispers of space dust and the echoes of ancient light. You're here beside me, and the universe is unfolding quietly, patiently, telling us its secrets one pulse at a time. There's so much more to explore: how pulsars guide spacecraft, how their signals might one day help us build a cosmic GPS, how these spinning stars connect us all across the vastness of space and time. But for now, let's linger in the silence, feeling the steady heartbeat of the universe in each distant pulse. It's a reminder that even in the darkest places, there is rhythm, there is order, and there is wonder. We are floating together, companions on a calm voyage through space, listening to the slow, steady dance of stars long gone, but never forgotten. Let's keep moving gently, companion, carried along by this quiet rhythm of the cosmos. Feel the vastness wrapping around us like a soft, dark blanket, sprinkled with shimmering dots, each one a sun, a story, a spark of light traveling through time and space to reach us. Now, think about the journey of a star that ends as a pulsar. Stars like our sun spend billions of years fusing hydrogen into helium, shining steadily. But the heavyweights, the massive stars, live fast and burn bright. When their fuel runs out, they collapse under their own weight in a dramatic explosion we call a supernova. It's as if the star blows itself apart in a cosmic firework, sending shockwaves rippling across space, seeding new clouds of gas and dust that will someday become new stars or planets. What's left behind is the star's core, crushed so tightly that it's no bigger than a city but packs more mass than our sun. That's a neutron star, and if it spins and beams radiation like a lighthouse, it's a pulsar. Imagine something so dense that a single teaspoon would weigh 1 billion tons. That's almost unimaginable, but that's the reality out here. As the core shrinks, it spins faster, sometimes hundreds of times per second. It's like an ice skater pulling in their arms and spinning faster on the rink. This rapid rotation, combined with the magnetic fields, creates those beams of energy sweeping across space. When those beams cross our line of sight, we see a pulse, a flash of light arriving in perfectly timed beats. This precise timing makes pulsars fascinating tools. For decades, scientists have used them to test the laws of physics under extreme conditions. Gravity so strong it bends light, matter so dense it defies ordinary understanding. And here's a fact to hold gently in your mind. Pulsars are so precise, some are more accurate than the best atomic clocks on Earth. They keep perfect time for millions of years, and that helps us measure vast distances and test the universe's secrets. You might wonder if pulsars ever stop spinning. They do, but it takes a long time, millions or billions of years. As they slow, their beams weaken, and eventually, they become silent. But before that, they often enter a graceful dance with companion stars. Some pulsars pull material from their partners, spinning faster and brighter. These are called millisecond pulsars, tiny cosmic metronomes racing at dizzying speeds. Picture that, a dead star resurrected, spun up like a top by a companion's gift, shining brightly again, It's a cosmic comeback story written in light and gravity. And what about the mysteries still unsolved? Pulsars sometimes glitch, unexpectedly speeding up or changing their pulse patterns. Scientists think this might be caused by shifts in their superdense interiors, like earthquakes on an alien world, but the details are still a puzzle. Each glitch is a whisper from the heart of these stars, inviting us to listen closer. Feel the quiet wonder here. We're companions on a voyage through time and space, touching things so extreme and strange, yet connected to us by the faint glow of understanding. So, my friend, let's keep drifting, feeling the slow, steady pulse of these cosmic lighthouses guiding us in the endless night. Because in their spin and shine, we find more than just science. We find connection. We find rhythm. We find the story of stars that lived, died, and yet still speak to us across the dark. And that story, that slow, steady pulse, carries on. Let's drift further, carried by the soft hum of the universe's timeless song. As we glide through this cosmic sea, think of the pulsar's pulses as a heart-beater reminder that even in the vast emptiness, there is life in the rhythm, a steady presence that echoes through time. Imagine standing beside one of these stellar remnants, not physically, of course, but in spirit, feeling the gentle vibration of its spin. Its magnetic field, invisible yet immense, reaches out like unseen arms, shaping the space around it. These magnetic forces accelerate particles, flinging them outward at incredible speeds, creating beams of energy that sweep across the cosmos. Picture those beams like cosmic lighthouses, flashing on and off with clockwork precision. If you were standing on a nearby world, you'd see the sky light up in sudden pulses, brief flashes of energy cutting through the darkness, a celestial Morse code from a distant past. It's fascinating that pulsars don't just exist in isolation. Some live in binary systems, locked in gravitational dances with companion stars or even other neutron stars. These dances can be wild and intricate, with pulsars and their partners circling each other at dizzying speeds, sometimes so close that they complete an orbit in mere hours. As they whirl, they send ripples through the fabric of space and time, itself gravitational waves, faint but powerful distortions traveling outward. Detecting these waves has opened a new window on the universe, letting us hear cosmic events that would otherwise be silent. And those waves connect us to the life and death of pulsars in an extraordinary way. When two neutron stars spiral together and merge, they create bursts of energy, so intense they briefly outshine entire galaxies. Those collisions forge some of the universe's heaviest elements, gold, platinum, and other seeding the cosmos with the building blocks of planets, and eventually, life. So, the story of a pulsar is intertwined with our own story, the story of the atoms inside us, forged in the hearts of stars long gone. That connection across billions of years and trillions of miles is both humbling and beautiful. Feel the quiet power of that link, the cosmic thread tying us to the ancient light flickering from these spinning stars. As we glide, you might notice how the pulsar's environment tells its own tales. Surrounding many pulsars are glowing nebulae, clouds of energized gas and dust, sculpted by the pulsar's winds and radiation. These nebulae shimmer with colors beyond what our eyes can see, glowing in X-rays and ultraviolet light. They're like cosmic paintings, shaped by invisible brushes wielded by stellar remnants. And the pulsar's wind streams of charged particles push against these clouds, carving tunnels and bubbles in the surrounding space. This ongoing interaction is a delicate dance, a push and pull that lasts thousands of years, slowly changing the landscape of space around the pulsar. We're witnessing not just the life of a star, but the ongoing shaping of the cosmos. Take a moment to imagine the vastness. Hear the pulsar spinning silently, its beams reaching across light years, its winds sculpting nebulae, its gravity warping the very space around it. And somewhere, on a tiny blue planet, we listen and learn, connected by the faint signals traveling through the darkness. Our journey is far from over. Beyond the pulsar, beyond the nebulae, the universe stretches endlessly, full of mysteries waiting to be explored. But for now, let's linger here, in the steady pulse of this cosmic lighthouse, feeling the quiet heartbeat of stars long gone, yet never truly silent. And so the story continues, a never-ending dance of light, spin, and Timian invitation to keep listening, keep dreaming, and keep wandering through the vast and beautiful universe together. Imagine the star before it became a pulsaran, enormous, fiery giant, tens of times more massive than our sun, burning bright with a fierce intensity. For millions of years, it has been churning away, fusing heavier and heavier elements deep inside its core. Eventually, it reaches a tipping point. Its fuel runs out, and gravity wins the battle. The core collapses suddenly, faster than you can blink. The outer layers explode outward in a supernova blast, lighting up the cosmos like a fireworks show that can be seen across galaxies. From this violent end, the core is left behind. What remains is no ordinary star. It's compressed into a sphere so dense that a single teaspoon would outweigh all the people on Earth combined. The atoms inside are crushed so tightly that electrons and protons merge, leaving mostly neutrons packed together in a way that defies everyday experience. This newborn neutron star is spinning incredibly fast, sometimes hundreds of times each second. Imagine an ice skater pulling in their arms and spinning faster. That's what's happening here on a cosmic scale. Its magnetic field, stronger than anything we can create on Earth, sweeps beams of radiation out across space. These beams flash past like the beam of a lighthouse, and when they cross our line of sight, we see a pulsy heartbeat from the remains of a star. Now, feel the vastness surrounding this spinning remnant, the quiet emptiness broken only by its rhythmic pulses. The star's energy isn't gone, it's transformed. It keeps spinning and shining in its own special way, a cosmic metronome ticking in the dark. This spinning, glowing beacon can last millions or even billions of years, gradually slowing down, but still sending its message across the void. Over time, the pulsar's beams weaken, but their story continues. Sometimes the pulsar is part of a duet, orbiting another star, locked in a dance of gravity and energy. These partnerships can lead to fascinating phenomena, like when a pulsar's strong gravity pulls material from its companion, spinning it up to dizzying speeds. These are called millisecond pulsars, some of the fastest spinners in the universe. It's almost like a cosmic remix, a dead star getting a second chance, spinning faster and glowing brighter thanks to its partner's gift. The universe has a way of recycling, reshaping, and surprising us in endless ways. And yet, pulsars are not just beautiful cosmic clocks. They are also laboratories for physics, under conditions we can't recreate on Earth. The immense density, gravity, and magnetic fields challenge our understanding of matter and space-time. Sometimes pulsars glitch, suddenly speeding up or changing their rhythm like a hiccup in the fabric of their being. Scientists study these glitches to peer inside the star's superdense core, trying to understand what's happening deep beneath the surface. As you listen, reach out and imagine the gentle pulse of the star, the rhythm echoing across billions of miles, connecting us to something both ancient and extraordinary. The universe speaks in these pulses, and we are fortunate to hear. Beyond the pulsar itself, its surroundings tell their own story. Many pulsars are surrounded by nebulae clouds of glowing gas and dust, energized by the pulsar's powerful winds and radiation. These nebulae shimmer in invisible light, glowing in X-rays and ultraviolet, painting cosmic pictures we can only glimpse with special instruments. The interaction between the pulsar's wind and surrounding material carves shapes and tunnels in space, a quiet but ongoing dance shaping the cosmos. Picture that vast, dark expanse, with the pulsar spinning at its center, its beams sweeping steadily, its winds sculpting the clouds around it. Somewhere far away, here on Earth, we listen and wonder, connected across time and space by the faint signals traveling through the void. As we continue our gentle journey, imagine the role these pulsars play in the grand cosmic tapestry. They're not just remnants, but active participants, shaping galaxies and even helping us map the universe. Because their pulses are so regular, astronomers use pulsars as precise cosmic clocks to measure distances, test theories of gravity, and search for ripples in space-time caused by colliding black holes billions of light-years away. In this way, pulsars are both messengers and tools, revealing secrets of the universe hidden beyond our everyday senses. And though their origins are violent, their presence brings a kind of calm order to the cosmos, a steady beat in the vast silence. So let's linger here in the pulsar's glow, letting its steady pulse remind us that even in the darkest corners of space, there is rhythm, there is light, and there is connection. The pulsar's pulse keeps ticking, a steady beacon shining through the vast emptiness, marking time in a place where time often feels meaningless. Imagine standing right beside this cosmic lighthouse, feeling the faint, almost imperceptible vibrations it sends out, echoes of a star's final moments and its new beginning. These tiny pulses are the universe's way of saying, "I am here, I persist." Now, think about how strange it is that such a small object can influence so much around it. Though just a few miles across, the pulsar's gravity is immense, curving space and tugging at anything that wanders too close. Around it, matter sometimes forms swirling disks, glowing with energy as the pulsar's magnetic fields twist and pull at them. These disks can flare suddenly, shooting out bursts of light and radiation that ripple across space like cosmic fireworks. In a way, pulsars are the universe's timekeepers. Their rhythm is so precise that we can use them to measure distances and even detect subtle ripples in the fabric of space-time. Picture yourself floating in a spaceship, guided by these distant clocks, navigating the vastness with the steady beat of pulsars as your compass. It's humbling to think how these remnants of exploded stars help us chart a universe so big it can feel overwhelming. And the story doesn't end there. Over millions of years, the pulsar slows, its spin gently winding down as it loses energy. But even then, it remains a sentinel, in the darker reminder of the cycles of creation and destruction playing out in the cosmos. Around us, the stars continue their own stories. Some will someday become pulsars themselves, while others will blaze their own unique paths through the universe. Each star is part of this vast cosmic dance, and by listening to the pulses of these spinning remnants, we hear a rhythm that connects everything. So here we are, drifting in space and time, wrapped in the pulse of a star that once was and still is, a small but mighty heartbeat in the endless dark. And as the pulse reaches us, faint and steady, it invites us to pause, breathe, and simply be present in the wonder of the universe. The pulse keeps rolling through the void, a soft, rhythmic tapping against the vast silence that stretches endlessly in all directions. Imagine the sheer persistence of this signal, billions of years traveling through empty space, passing by planets, stars, and clouds of cosmic dust, until finally reaching us here, listening quietly. What's remarkable is how much this tiny spinning star can tell us. Its pulse is like a code, a story woven into light and radio waves. Scientists tune in, deciphering these messages to understand the nature of matter under unimaginable pressure, the behavior of magnetic fields billions of times stronger than Earth's, and even the very fabric of space-time itself. Let your mind wander to the environment around the pulsar. There's often a ghostly glow, a nebula of energized gas that the pulsar's fierce winds have swept up and shaped. These ethereal clouds drift and shimmer, sculpted by invisible forces, painting patterns only the universe could imagine. The light they emit is often outside the visible spectrum, invisible to human eyes, but captured by specialized telescopes. In these quiet colors, the pulsar's presence is made visible, a lighthouse surrounded by a glowing sea. Sometimes, two pulsars orbit one another in a tight cosmic waltz. Their gravitational dance is a spectacle beyond imagining, a duet that warps time and space, pulling and spinning in perfect rhythm. By watching their interactions, we glimpse the workings of gravity in its most extreme form, testing ideas about the universe that even Einstein pondered. Pause for a moment and picture the enormity of these forces, the strength needed to collapse a massive star's core, the speed at which the pulsar spins, the vast distances its beams travel. And yet, despite all this power and motion, from where we sit, it feels calm, almost gentle. There's a poetry in that contrast, the violent birth of the pulsar and the soft, steady beat it sends out across the cosmos. It's a reminder that the universe is full of stories waiting to be heard, if only we listen closely enough. And so, the pulsar continues, spinning and pulsing, a cosmic heart beating in the silence. We float alongside it, companions in time and space, wrapped in the quiet glow of stars and the deep, slow music of the universe itself. Let's keep moving gently alongside this cosmic marvel. The pulsar's heartbeat pulses out with such precision that some of them are as reliable as the best clocks we've ever made. Imagine a clock so exact that if you used it to keep time, you'd lose only a tiny fraction of a second over millions of years. That's the kind of accuracy these spinning stars achieve, thanks to their incredibly steady rotation. This precision comes from the pulsar's extreme density. Picture something with the mass of about 1.5 times our Sun, compressed into a sphere barely 20 kilometers wide that's like squeezing Mount Everest into a marble. This unimaginable density means the star's matter is crushed into neutrons packed tightly together, a state of matter not found naturally on Earth. It's why pulsars are sometimes called neutron stars. As the pulsar spins, it also loses energy. This energy escapes as beams of electromagnetic radiation shooting out from the magnetic poles. Because the magnetic axis isn't aligned perfectly with the rotational axis, these beams sweep across space, like the rotating light of a lighthouse. When one of these beams points toward Earth, we detect a pulsar, hence the name pulsar. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, who noticed regular pulses coming from space while studying radio waves. At first, the pulses were so regular and mysterious that they were jokingly called little green men, as if they were signals from an alien civilization. But as more pulsars were discovered, scientists realized these signals were natural and revealed a whole new class of celestial objects. Beyond the steady pulses, some pulsars exhibit sudden changes called glitches. These glitches cause the star's spin rate to jump slightly, likely due to sudden rearrangements in the star's crust or interior. It's as if the pulsar hiccups, and these rare events provide clues to the star's internal structure, which we can't observe directly. Pulsars also serve as cosmic laboratories, helping us understand physics under conditions impossible to replicate on Earth. By studying pulsars, scientists test theories of gravity, nuclear physics, and the behavior of matter at its densest. Surrounding many pulsars are nebulae clouds of gas, energized by the pulsar's wind of particles moving at nearly the speed of light. These pulsar wind nebulae glow brightly in X-rays and radio waves, creating intricate patterns shaped by the pulsar's rotation and magnetic fields. Imagine the vastness of these structures, stretching light years across space, all powered by the energy of a star no larger than a city. It's a reminder that even the smallest objects in space can have a huge influence on their surroundings. As we drift here, the pulse continues, a steady heartbeat in the silent dark, carrying stories older than any of us can fully grasp. The pulsar spins on, a cosmic timekeeper, a beacon in the night, inviting us to listen ever closer. Let's drift deeper into this silent sea, where the pulse becomes a steady rhythm beneath the vast cosmic canopy. Imagine yourself here beside this tiny, dense star, no bigger than a small city but holding the weight of the sun's life all packed into a sphere so tight it's almost unreal. Reach out and feel the faint tug of gravity stretching from this spinning heart, pulling softly at the very fabric of space around it. Look closely, and you'll see the magnetic fields spiraling out like invisible ribbons, twisting and curling far beyond the star's surface. They reach like fingers into the darkness, grabbing charged particles and flinging them outward at nearly the speed of light. These particles race along the magnetic highways, spiraling toward the star's poles where they burst into energetic beams. Picture these beams sweeping past you like a lighthouse beam cutting through a foggy night, each flash a reminder of this star's relentless spin. Listen to the silence between pulses. It's not empty, it's full of the quiet hum of the universe carrying this ancient signal across the vast gulf of space. The pulsar's pulse is a steady heartbeat, a cosmic rhythm that connects us here, on our little blue planet, to events that happened millions of years ago, in a corner of the galaxy far from our own. Feel the awe as you realize that the pulse you detect is a photon born from the death of a massive star, now transformed into a beacon of light and energy. The explosion that created the pulsar was one of the most violent moments in the cosmos, a supernova so powerful it briefly outshone entire galaxies. But from that chaos came this precise, steady spin, a heartbeat that continues long after the fire has faded. The pulsar's life is a story of balanced gravity pushing inward, magnetic forces pushing outward, rotation keeping the whole thing alive. It's a fragile dance, and yet it can last for millions of years, a cosmic metronome marking time in the infinite night. Imagine watching a pulsar slow down very gradually, its pulse stretching out as energy leaks away. Sometimes, sudden glitches jolt the star, spinning it up unexpectedly before the steady slowing continues. These are moments of mystery, clues from the hidden interiors of these stars, offering us a glimpse behind the cosmic curtain. Now, picture a pulsar locked in a gravitational dance with another star, spinning faster and faster as it pulls matter from its companion. These millisecond pulsars are cosmic sprinters, spinning hundreds of times each second, their pulses racing by like rapid-fire drumming. They are cosmic marvels, pushing the boundaries of what matter and energy can do. As we float here, suspended in space and time, you can almost feel the delicate balance of forces holding this star together: the push and pull, the fierce magnetism, the spinning energy. It's a quiet power, a gentle might that hums softly through the dark. We are companions in this vast silence, sharing the pulse, the glow, the endless mystery of a star that lives on in light. And as we listen, we become part of its story, witnesses to the quiet, persistent heartbeat of the cosmos itself. The pulsar's spin is an extraordinary phenomenon. Imagine a star, once massive and fiery, collapsing suddenly into a sphere so dense that a teaspoon of its material would weigh 1 billion tons on Earth. This collapse spins it up like a cosmic top, twisting faster and faster until it blazes through space, rotating dozens, sometimes hundreds of times every second. Picture the sheer energy packed into this tiny ball, the forces at play twisting and squeezing matter into states that challenge our imagination. Surrounding many pulsars, there's a glow nebulae formed from particles accelerated by the pulsar's magnetic fields. These nebulae aren't static, they ripple and shimmer, swirling with color beyond our normal sight, glowing in X-rays and radio waves. Imagine drifting through such a nebula, feeling the gentle push of charged particles streaming past you, the invisible winds of a star's ghostly breath. It's like standing inside a shimmering, ethereal ocean of energy. Now, shift your gaze to the broader picture. Pulsars often emerge from massive stars that once lived brilliant, if short, lives. When such a star reaches the end of its life, it explodes in a supernova, of the most powerful explosions in the universe. This blast scatters stellar material outward, seeding the cosmos with the elements that make planets and life possible. The leftover core, crushed and spinning, becomes the pulsar. Think about the journey of that core, how it collapses, how its rotation speeds up, how its magnetic field intensifies. It's a transformation from fiery giant to a compact, spinning beacon. And through it all, the pulsar sends its signal, a rhythmic flash across light years of darkness, steady and precise. As the pulsar spins, its beams sweep across space like the hands of a cosmic clock. If you imagine yourself floating nearby, you'd see the beam flash past you again and again, a gentle, pulsing light marking the passage of time. This light can be seen in radio waves, visible light, X-rays, and even gamma rays. Different pulsars shine in different colors of light, revealing layers of their complex nature. Sometimes pulsars come in pairs, locked in a gravitational embrace with another star or even another pulsar. These binary systems twist and turn in cosmic dances, drawing closer as they lose energy, until they merge in spectacular events that send ripples through space-time itself. These ripples, called gravitational waves, were predicted over a century ago and only recently detected by us here on Earth. Imagine being present to witness such a cosmic duet, where the final moments are so powerful they shake the very fabric of the universe. The story of pulsars is also a story of discovery. Since the first was found over 50 years ago, thousands have been detected, each with its own pulse and personality. They've helped us map our galaxy, test the limits of physics, and even search for planets orbiting far-off stars. Yet for all we know, there's still so much mystery. What lies deep inside a pulsar's core? How exactly do the glitches occur? Could pulsars help us understand the nature of matter and energy at their most extreme? These questions keep scientists listening to the sky, tuning into the pulses, hoping for new answers. And so, as the pulse pulses on, we drift with its companions in space and time, sharing a moment with one of the universe's most fascinating remnants. It's a journey that stretches across billions of years and light years of space, a quiet story told in flickers of light and the steady beat of a star that refuses to fade away. Let's continue floating alongside this cosmic heartbeat, where time stretches and the pulse of the pulsar becomes a soft drum guiding us deeper into the mysteries of the universe. Imagine the star's rotation a fierce, unyielding spin born from a catastrophic end, yet creating a rhythm that speaks of resilience and transformation. This tiny beacon, no larger than a city, tells tales of immense power contained in the smallest corners of space. Picture the immense gravity that holds the pulsar together. It's a gravity so strong that it warps space itself, bending the path of light and matter around it. This warping creates strange effects, like light that curves and dances as it escapes the pulsar's grip. If you were close enough, you might see the star's surface warped into shapes and patterns unlike anything on Earth, a shimmering sphere that seems to pulse with energy from within. The magnetic field lines sweep out far beyond the star's surface, tangled and twisted by the rapid spin. These magnetic fields are unimaginably strong, trillions of times stronger than the magnetic field on Earth. They guide particles hurtling away at nearly the speed of light, carving out vast regions of energized gas and plasma. These areas glow brightly in high-energy light that our eyes cannot see, but special instruments reveal a landscape as dramatic as any on Earth, with jets, arcs, and wisps swirling in an intricate cosmic dance. Among these charged particles are electrons and their counterparts, positrons, racing along the magnetic field lines and creating bursts of radiation that flash past us in steady pulses. It's a dance choreographed by forces beyond human imagination, yet the pattern is so steady, so precise, it becomes a cosmic metronome. As the pulsar spins and pulses, it gradually slows down, losing energy in a slow cosmic sigh. This slowing can take millions of years, a gentle deceleration that marks the star's long farewell. But sometimes the pulsar surprises us with sudden jumps in its spin rate glitches that hint at the star's complex inner workings. Scientists think these glitches may be caused by starquakes or sudden shifts in the superdense matter inside the star, where neutrons are packed so tightly that the star's crust cracks and rearranges itself. Beyond the star itself, the pulsar's influence shapes its surroundings. The pulsar wind a stream of charged particles moving near the speed of light pushes against the remnants of the star's explosive birth, creating pulsar wind nebulae. These nebulae are vast and beautiful, glowing clouds that shimmer in energetic light and tell stories of the pulsar's fierce winds and magnetic might. Imagine drifting through one of these nebulae, feeling the gentle push of charged particles against you, floating inside a glowing cocoon formed by the star's breath. Many pulsars exist in binary systems, locked in gravitational embraces with companion stars. In these systems, the pulsar can pull material from its partner, creating swirling disks of gas that spiral down onto the pulsar's surface. This accretion can spin the pulsar up to dizzying speeds, turning it into a millisecond pulsar cosmic speedster spinning hundreds of times per second. The energy released in these systems can be immense, lighting up the surroundings in X-rays and gamma rays. The story of a pulsar is a story of extremes: extreme density, extreme magnetism, extreme speed. Yet from these extremes emerges a rhythm that connects us, a steady pulse that travels across vast cosmic distances to reach our instruments and hearts. These pulses carry whispers from the far reaches of our galaxy, messages from stars that once burned bright and fierce, now spinning quietly in the cosmic night. As we float here, companions in space and time, you can almost feel the gentle energy of this pulsar pulsing through the darkness. It's a reminder that even in the vast silence of space, there is movement, there is life, and there is story. The pulse is an echo of creation and destruction, of balance and change, a cosmic heartbeat inviting us to listen and wonder. Feel how the pulsar's energy reaches beyond itself, shaping its neighborhood in space. The particles streaming outwards interact with clouds of gas and dust left over from the star's explosive birth, creating glowing shells and filaments that ripple like waves across the cosmic ocean. These structures aren't static. They shift and shimmer, pushed and pulled by magnetic fields and charged winds. It's like watching the universe breathe, exhale, and pulse along with the star's rhythm. Now, let's imagine the environment closer to the pulsar's surface. The crust is a thin, incredibly strong shell of neutrons packed tightly together, but beneath it lies a superfluid core matter in a state that defies normal physics, flowing without friction or resistance. This inner dance plays a role in the glitches we sometimes detect, sudden shifts that tell us the pulsar's interior is as dynamic and alive as the signals it sends. Pulsars also serve as cosmic laboratories for physics, pushing our understanding of matter, energy, and space-time. By studying the timing of their pulses with extreme precision, scientists can test the very foundations of gravity and relativity. Some pulsars, especially those in binary systems, act as natural clocks that help detect the ripples of gravitational waves, those subtle tremors in space-time caused by cataclysmic events like black hole collisions far away. Imagine drifting alongside a pair of pulsars locked in an orbit so tight they circle each other in just a few hours. Their pulses arrive like interwoven beats, a complex rhythm of light and time, echoing the violent past that brought them together. Observing such systems gives us a glimpse into the future of the cosmos, where collisions and mergers reshape galaxies and create bursts of energy that ripple across the universe. As you float here beside me, you might notice that pulsars come in many varieties, some slow and steady, others spinning wildly fast, some shining mostly in radio waves, others glowing fiercely in X-rays and gamma rays. Each pulsar has its own personality, its own story carved into the fabric of space-time. Picture the path of a pulsar traveling through space after the supernova explosion that birthed it. These stars often receive a kick, a violent shove that sends them careening through the galaxy at hundreds of kilometers per second. They're cosmic wanderers, moving through star fields and interstellar clouds, carrying their pulses like distant signals from a restless traveler. And what of the future for these spinning stars? Over millions of years, the energy radiated by pulsars dwindles, their spins slow, and their magnetic fields weaken. Eventually, they become what we call dead pulsars, quiet, dark remnants that no longer flash their beams across the cosmos. But even then, their story doesn't truly end. Their material remains part of the cosmic cycle, contributing to new stars, planets, and perhaps even life itself. Let's keep drifting in this vast ocean of space, carried gently on the waves of light and shadow cast by these extraordinary stars. Think about the way a pulsar's pulse reaches us steady, reliable, like the ticking of a cosmic metronome that has been keeping time for millions, sometimes billions, of years. That pulse travels through vast stretches of empty space, crossing unimaginable distances to reach our instruments here on Earth. Feel how that journey is a message, a story carried in waves of energy. Every pulse is a heartbeat from the distant past, telling us about the star's life, its explosive death, and its ongoing dance in the galaxy. Sometimes the pulses arrive so regularly that scientists use pulsars as natural clocks, timing experiments that test the limits of physics, like the ripples in space-time caused by colliding black holes. Imagine now the environment around a young pulsar. The explosive supernova that birthed it didn't just leave a compact star behind. It scattered a cloud of gas and dust outward, creating a glowing nebula. This nebula is a place of chaos and beauty, filled with charged particles racing at nearly the speed of light. The pulsar's powerful magnetic field funnels these particles into jets and winds, sculpting the nebula into intricate shapes that shimmer in wavelengths beyond human sight. As we float near this nebula, listen for the subtle hum of particles colliding, the faint glow of energized gas, the invisible winds pushed by the pulsar's magnetic breath. This is the star's voice after the storm, a soft yet persistent presence in the vast cosmic dark. Consider how some pulsars spin so rapidly they complete hundreds of rotations each second. These millisecond pulsars are cosmic speed demons, often recycled by stealing material from a companion star. This accretion process transfers angular momentum, spinning up the pulsar to incredible speeds. Picture this tiny star whirling like a dancer, its magnetic poles sweeping space with beams of radiation. Even as the pulsar spins, it slowly loses energy. That loss of energy causes the star to gradually slow, its pulse spacing lengthening over millions of years. Sometimes, however, the pulsar suddenly jumps to a faster spinor glitch, likely caused by the internal rearrangement of the star's super-dense matter. These glitches remind us that beneath the steady pulse lies a dynamic, shifting core. Pulsars also guide us to deeper mysteries. Their extreme density compresses matter beyond what can be replicated on Earth, making them natural laboratories for studying the laws of physics under conditions impossible to create otherwise. By listening carefully to their pulses, scientists test theories about gravity, quantum mechanics, and the nature of matter itself. Drifting further, think about the role pulsars play in the grand cosmic cycle. The heavy elements forged in the supernova that births a pulsar elements like iron, calcium, and oxygen seed the galaxy. These elements eventually become part of new stars, planets, and maybe even the building blocks of life. The pulsar is both an end and a beginning, a testament to the endless recycling of matter in the universe. As we float here in the quiet dark, you can imagine the vast distances between us and these stars, yet feel the closeness brought by their steady, rhythmic pulses. They are timekeepers, storytellers, and cosmic lighthouses in the vast sea of space. Let's keep floating alongside this quiet cosmic rhythm as the pulsar's steady pulse continues to guide us through space and time. You might wonder how dense these stars really are. Imagine squeezing a mass greater than our Sun into a sphere only about 20 kilometers across roughly the size of a small city. That's the pulsar's size, yet it packs in more matter than millions of Earths combined. This extraordinary density means a single teaspoon of pulsar material would weigh about 1 billion tons here on Earth. It's almost unimaginable, yet it's a reality out there, spinning silently in the void. As we drift, consider the magnetic field again, the strongest known in the universe. Pulsar magnetic fields can reach strengths up to 1,000 trillion times stronger than Earth's. These fields shape the charged particles around the star and create the beams of radiation we detect as pulses. These beams sweep across space like lighthouse beams, and if Earth happens to lie in their path, we see the star blinking on and off in a cosmic signal that can last for millions of years. Some pulsars are found in clusters of stars called globular clusters, densely packed spheres orbiting the outskirts of galaxies. In these clusters, stars interact closely, and pulsars often form through dynamic encounters, sometimes gaining companions or swapping partners in a stellar dance. These environments produce millisecond pulsars, some spinning over 700 times per second, the fastest known natural spinners in the universe. Pulsars are also natural gravitational wave detectors. By carefully timing their pulses, astronomers can detect tiny disturbances in space-time caused by gravitational waves passing between Earth and the pulsar. This method has helped confirm Einstein's theory of general relativity and opens windows to observing massive events like black hole mergers that happen far, far away. Look at how pulsars form in binary systems. Sometimes, a massive star in a pair explodes, leaving behind a neutron star that's still bound to its companion. Over time, material can flow from the companion star onto the neutron star, heating up and causing the pulsar to emit X-rays in addition to radio waves. These X-ray pulsars tell us about matter under extreme gravity and magnetic fields, helping us understand how physics behaves in such exotic settings. Then there are magnetars, a special kind of pulsar with magnetic fields even stronger than typical pulsars, up to 10,000 times stronger. These stars occasionally release huge bursts of energy, brighter than the sun's output in hundreds of thousands of years, creating starquakes that shake their surfaces and send ripples through space. Although magnetars are rare, their powerful outbursts remind us how energetic and unpredictable the universe can be. Pulsars also help us map our galaxy. By measuring their positions and motions, we can trace the spiral arms of the Milky Way and learn about its structure and history. They act as cosmic signposts, shining beacons in the darkness that mark where massive stars once lived and died. As we move farther from the pulsar, the space around it is still influenced by its past. The supernova remnant, glowing softly in X-rays and visible light, tells a story of violent birth and gradual fading. These remnants enrich the interstellar medium with heavy elements that become the seeds for new stars, planets, and eventually, life. It's a reminder that endings in space are often new beginnings. Now imagine the lifespan of a pulsar, typically tens of millions to 100 million years. That might seem long to us, but in cosmic terms, it's relatively brief. After this time, the pulsar slows down and its beams dim, until it no longer pulses in detectable light. It becomes a quiet neutron star, still dense and mysterious, drifting through the galaxy, a ghost of its former energetic self. Yet even in its silence, the pulsar's legacy endures. Its matter and energy have shaped the cosmos, from star clusters to planets. Somewhere, Perhaps in a distant star system, the elements forged in these ancient explosions form the building blocks of new worlds, maybe even life itself. So, as we continue our journey together, let the pulsar's story be a reminder of the incredible forces at work in the universe, forces that spin and pulse quietly in the night, connecting us all in a grand cosmic dance of creation, destruction, and rebirth. The dense core of the pulsar, formed in that titanic stellar explosion, remains one of the universe's most fascinating objects. Imagine matter packed so tightly that a sugar cube-sized piece would outweigh a mountain here on Earth. This matter is mostly neutrons, particles usually found inside atomic nuclei, but crushed together on an unimaginable scale. It's a strange state, one that pushes the limits of physics and challenges our understanding of what matter can do. The pulsar's magnetic field wraps around it like an invisible cocoon, twisting and turning as the star spins. These fields are billions of times stronger than anything we experience on Earth and are responsible for the beams of radiation that sweep across space. When one of these beams crosses our line of sight, we see a pulse of light, like a cosmic lighthouse sending a steady signal through the dark. Sometimes these pulses come with surprising quirks. The spin rate of a pulsar is not always perfectly steady. Occasionally it shifts suddenly, speeding up in what scientists call a glitch. These glitches reveal that beneath the surface, the star's superdense interior is far from calm. There are shifts and movements inside the core that can affect the rotation, letting us peer into the physics of matter under extreme conditions. Picture the path of a pulsar speeding through the galaxy. When the original star exploded, it often gave the newborn neutron star a powerful kick, sending it careening through space at hundreds of kilometers per second. These runaway stars blaze a trail through the interstellar medium, their magnetic fields and particles interacting with clouds of gas and dust, shaping the environment around them. Some pulsars form in binary systems, locked in an orbit with another star. In these cosmic duets, the pulsar can pull material from its companion, forming an accretion disk swirling around it. This matter heats up as it falls inward, glowing brightly in X-rays and feeding the pulsar's magnetic activity. In some cases, this process spins the pulsar up to incredible speeds, creating millisecond pulsars that rotate hundreds of times each second. As the pulsar's energy slowly fades, its spin rate decreases. Over millions of years, it grows quieter, until it becomes what's sometimes called a dead pulsar neutron star, no longer flashing its beams toward Earth. But even then, the star continues its silent journey through the galaxy, a remnant of the violent death of its predecessor. Despite their small size, pulsars affect their surroundings dramatically. The particle winds they emit push on surrounding gas and dust, creating shock waves and glowing nebulae that stretch across light years. These nebulae are living monuments to the star's explosive birth and ongoing energy output, glowing softly in multiple wavelengths invisible to the human eye. And beyond their physical effects, pulsars serve as natural laboratories, helping us test ideas about gravity, matter, and the very nature of space and time. Their precise pulses allow scientists to measure the tiniest changes in distance and time, confirming predictions made by Einstein and revealing new mysteries about the cosmos. The pulsar's story is one of extremes of unimaginable density, ferocious magnetic fields, and spins so rapid they defy everyday experience. But it's also a story of connection, how remnants of dead stars continue to influence the universe long after their fiery deaths. The star's pulse continues to echo across the cosmos, a reminder of the ongoing cycle of birth, death, and transformation that shapes everything we see. The story doesn't end here, and the pulsar's light will keep reaching out across space and time, waiting for curious minds like ours to listen and learn. As we linger in the quiet glow cast by the pulsar's ancient heartbeat, it's fascinating to imagine how this tiny stellar ember fits into the grand tapestry of the cosmos. While it's small only about the size of a city, the pulsar's influence stretches far beyond its physical boundaries. The energy it releases shapes its neighborhood in space, sometimes creating spectacular nebulae that shimmer in colors and lights invisible to our eyes, but breathtaking when seen through special telescopes. Picture the glowing tendrils of a pulsar wind nebula stretching out, sculpted by the star's magnetic winds, pushing and pulling on the gas and dust around it. These glowing clouds serve as a reminder that even after the dramatic death of a massive star, life in space continues, albeit in forms we might never have expected. The pulsar isn't just a leftover, it's a creator, an architect of cosmic beauty that unfolds over thousands of years. And yet, even as the pulsar spins tirelessly, its energy output slowly wanes. The immense forces that fuel its rapid rotation and intense magnetic field aren't eternal. Over time, the pulsar's spin slows, its pulses become weaker, and eventually, it drifts into silence. But that silence is not the end of the story. The pulsars matter: its neutrons, its magnetic fields, its energy are all part of a larger cosmic cycle. Consider that the heavy elements forged in the supernova explosion, the iron, the nickel, and other seed the galaxy, drifting outward in space and time. These elements become part of new stars, planets, and possibly even life itself. In this way, the pulsar's life and death contribute to the ongoing evolution of the universe, a vast web of creation and destruction that spans billions of years. It's humbling to think that the atoms in our bodies might have once been part of such an extraordinary star. Pulsars, in their quiet, spinning glory, are echoes of the universe's grand story, a story of transformation, endurance, and connection. So, as we drift here in this gentle cosmic sea, surrounded by the faint glow of distant stars and the whisper of ancient pulses, I invite you to feel that connection. Reach out with your imagination and sense the vastness, the mystery, and the endless beauty of the universe, carried on the steady rhythm of a pulsar's heartbeat. We're part of this cosmic dance, companions on a journey that stretches across space and time. The pulsar's story continues to unfold, an ongoing chapter in the ever-expanding book of the cosmos, and together, we will keep listening. As we remain here, cradled in the vast silence between stars, the pulsar's steady beat reminds us of nature's extraordinary resilience. It's astonishing to think about how these dense remnants of exploded stars persist through eons, spinning with such precision that they rival the most advanced clocks we've built on Earth. Their pulses are so regular that astronomers use them as cosmic timekeepers, measuring time with incredible accuracy. This precision helps us explore mysteries beyond our solar system and even test the very fabric of space and time. Imagine the patience needed to listen to these cosmic metronomes, their pulses ticking rhythmically as the galaxy spins around us. Each pulse is a tiny messenger, a signal that has traveled hundreds or even thousands of light years through the dark expanse of space to reach us. The sheer distance those signals cross makes every one of them feel like a miracle, a whisper from the universe's distant past carried on a beam of light. Now, picture yourself drifting alongside the pulsar, carried gently on the invisible winds of charged particles it releases. These winds interact with the surrounding interstellar material, creating glowing bubbles of energized gas and dust that expand outward. Over time, these bubbles can stretch for dozens of light years, glowing faintly in radio waves and X-rays. It's a slow, graceful dance of energy and matter, unfolding on a scale that dwarfs human lifetimes. And here's something to wonder about. While pulsars are typically lonely travelers, sometimes they form fascinating pairs with other stars. When locked in a binary orbit, pulsars and their companions can exchange matter and energy in a delicate cosmic relationship. This interaction can spin up the pulsar to dizzying speeds, making it pulse hundreds of times each second. These millisecond pulsars are among the fastest known spinning objects in the universe, their rotation so rapid that a day on one would last mere milliseconds by our clocks. The dynamics of these stellar duos offer clues about how stars evolve and interact over millions of years. They also act as natural laboratories for extreme physics, where gravity, magnetism, and matter collide in ways we cannot recreate on Earth. Watching how these systems change teaches us more about the universe's fundamental laws and the extraordinary outcomes of stellar life cycles. As the pulsar continues its journey, it also plays a role in shaping the galaxy itself. By tracing the positions and movements of pulsars, astronomers map the spiral arms of the Milky Way and understand the history of star formation in our cosmic neighborhood. Each pulsar is like a breadcrumb left behind by massive stars that once lit up the galaxy, telling a story of birth, death, and cosmic renewal. And speaking of renewal, the story of pulsars ties deeply into the grand cycle of matter in the universe. The elements expelled in supernova explosions, the very materials that make up planets and life, are scattered across space, eventually coalescing into new stars and worlds. This ongoing recycling process means that in a very real sense, pulsars and their progenitor stars have a hand in crafting the very fabric of the cosmos we live in. So, as we hover in this quiet cosmic expanse, take a moment to absorb the vastness and the connection we share with these distant remnants. The pulsar's pulse is a rhythm of the universe itself, steady and enduring, a constant companion on our journey through space and time. It's a reminder that even in the darkest, most remote corners of the cosmos, life of a shortened energy persists, spinning stories across the eons. Our journey alongside the pulsar is not just a tale of death and decay, but of transformation and ongoing influence. The universe never truly forgets, and neither do these spinning stars. They keep sending their light, their pulse, their message, out into the infinite, inviting us to listen, to wonder, and to keep exploring. Let's shift our gaze now, drifting beyond the familiar Milky Way, out toward the farthest reaches of the universe where quasars reign supreme. Imagine standing at the edge of a vast cosmic ocean, watching a lighthouse so bright that it outshines entire galaxies. That's a quasar, brilliant beacon fueled by a monstrous black hole at the center of a distant galaxy, spinning and pulling in matter with unimaginable force. Picture this: a supermassive black hole millions or even billions of times the mass of our Sun, surrounded by a swirling disk of gas and dust. This disk isn't calm. It roars with energy as gravity drags matter inward, heating it to temperatures hotter than anything we can experience on Earth. The intense heat causes the disk to glow fiercely, pouring out light across the electromagnetic spectrum from radio waves to X-rays, making quasars some of the brightest objects in the universe. Imagine the energy pouring from this cosmic engine, far greater than the combined light of the billions of stars in the host galaxy. That light travels across billions of light years, reaching us as a faint, distant glow. When we look at quasars, we're actually looking back in time, glimpsing the universe as it was when it was young and wild, less than 2 billion years old. The power of a quasar is staggering. Some can emit energy equivalent to 1,000 Milky Ways combined. Yet, despite this overwhelming brightness, quasars are incredibly compactful, that energy concentrated in a region smaller than our solar system. It's a reminder of how the universe loves extremes, colossal mass packed into tiny spaces, creating phenomena that stretch our understanding. Sometimes quasars unleash jets of particles traveling near the speed of light, shooting out from the poles of the black hole like cosmic fire hoses. These jets extend for thousands of light years, punching through space and shaping their galactic environments. They stir up the gas in the galaxy, influencing the formation of new stars or sometimes shutting it down altogether. It's a cosmic feedback, loop, powerful, dramatic, and complex. Think about the role quasars play in the grand scheme of cosmic evolution. They mark a phase in galaxy growth, where the central black hole is feeding aggressively, lighting up the cosmos and impacting everything around it. Quasars are like celestial engines, regulating the life cycles of galaxies, and in doing so, shaping the universe's large-scale structure. Despite their power, quasars don't last forever. Over time, as the black hole consumes the available gas, the brightness fades, and the quasar transitions into a quieter phase. Yet the imprint of its energy remains, leaving clues about the early universe that astronomers piece together, like cosmic detectives. So, as we float near this blazing beacon, listen to the echoes of creation and destruction it carries across the vast darkness. The quasar's light is a message from a distant past, inviting us to explore the fierce beauty and raw power that shaped galaxies and, ultimately, our cosmic neighborhood. From the whispering pulse of a distant neutron star to the roaring blaze of a quasar, the universe tells its story in waves and light, in rhythms both subtle and spectacular. And here we are, drifting along with it, companions on an endless voyage through space and time. Feel the immense scale around us as we hover near this quasar's radiant heart. The swirling disk of superheated gas, spinning faster and faster as it feeds the black hole, creates a cosmic furnace that radiates energy so powerful it can be detected across billions of light years. Imagine the light taking that long to reach our eyes, a flicker from the ancient universe, telling tales from a time when galaxies were young and the cosmos was still finding its shape. As we drift gently alongside this distant beacon, you might sense the incredible forces at play. Gravity, so intense it warps space itself, magnetic fields twisting and snapping, unleashing torrents of particles that shoot out into the void at nearly the speed of light. These jets carve through intergalactic space like giant cosmic blowtorches, stirring the gas between galaxies, shaping star formation, and sculpting the vast cosmic web that threads the universe together. Quasars, in their violent brilliance, are among the universe's great engines of change. Their energy output can blow away gas clouds, halting the birth of new stars in their host galaxies, or sometimes compress gas to spark new stellar nurseries. This push and pull influences how galaxies grow and evolve over billions of years. What seems like destruction is also a form of creation, a cosmic balancing act, choreographed by gravity and energy. While we are bathed in the glow of the quasar's light, think about its journey. Each photon began its voyage deep inside that maelstrom of matter swirling around the black hole's edge. Some photons escaped immediately, others bounced and scattered, trapped briefly before bursting free into the universe. Now, traveling across eons of space and time, these photons carry with them a story, a record of extreme physics, of matter pushed to its limits, and of the colossal forces that shape the cosmos. It's humbling to realize that what we see is only a snapshot. The quasar's brilliance will fade as the black hole's feast slows. Gas runs out, the accretion disk cools, and the once dazzling beacon dims to a quiet, almost invisible point. Yet, even in its twilight, the quasar leaves behind marks, ripples in gas, trails of high-energy particles, and shifts in the galactic environment that tell astronomers about the universe's history and the life cycle of galaxies. As we slowly pull away from this blazing lighthouse, let your imagination follow the path of those jets, stretching far beyond the galaxy, carrying energy and matter into the vast darkness. These cosmic lighthouses help light the way for our understanding, guiding us through the mysteries of space and time. From the tiny, spinning heart of a pulsar to the blazing core of a quasar, the universe whispers its secrets to those who listen closely. Together, we've floated through extremes of density, speed, and energy, witnessing how the remnants of stars, both small and supermassive, continue to shape the cosmos in surprising ways. So here we are, companions on this endless voyage, wrapped in the glow of distant lights, pulsing rhythms and cosmic winds. The universe's story is far from finished, and the more we explore, the more wondrous mysteries unfold before us. With every pulse, every flash, and every shimmer, we are reminded of our place in this vast, beautiful expanse of curious travelers, sharing the silent music of the stars. As we drift further, bathed in the faint glow of countless stars and the soft whisper of cosmic winds, it's incredible to think how these extraordinary objects, the pulsars spinning tirelessly, and the quasars blazing fiercely, are threads in the vast, interconnected tapestry of the universe. Each one tells a unique story, yet together they form a grand narrative about how matter, energy, and time weave through space. Imagine the pulsar again, that tiny, dense remnant of a once mighty star, spinning with such precision it could rival the most accurate clocks humans have ever made. Its pulses are more than just light, they're cosmic beacons guiding us through the darkness, marking time on a scale unimaginable here on Earth. The neutron star's intense magnetic field sweeps through space, sending out radio waves and X-rays that tell us about the extreme physics inside and around it. On the other hand, the quasar, powered by the insatiable appetite of a supermassive black hole, reminds us of the universe's capacity for brilliance and transformation. It's a furnace burning with the energy of billions of suns, a beacon from the early universe, lighting the path to our cosmic origins. The jets spewing out at near light speeds, carving into the surrounding space, show us how powerful forces shape the galaxies, and by extension, the universe itself. Both these objects, sown small and dense, the other vast and overwhelmingly bright, demonstrate nature's love for extremes. They are the aftershocks of creation and destruction, the lasting echoes of stellar death and cosmic birth, continually influencing their surroundings in subtle and dramatic ways. Think of the life cycle of stars like an endless symphony. Massive stars live fast and die young, ending in spectacular explosions that scatter the elements necessary for life. From their ashes emerge pulsars, spinning relics holding clues to the most extreme states of matter. Meanwhile, galaxies with supermassive black holes at their centers ignite into quasars, shaping their environments and illuminating the distant past. Every time we observe these phenomena, we're peering deeper into the universe's memory, catching fragments of a story billions of years in the making. It's a story of transformation, where death leads to new beginnings, where energy flows and reforms, and where the cosmos continually reinvents itself. So, as we continue floating in this cosmic sea, take a moment to feel the vastness and wonder. Reach out and imagine the gentle pulse of the neutron star beside us, steady and unyielding. Hear the faint hum of the quasar's radiant energy far away, its light stretching across space and time to greet us here and now. Together, these celestial wonders invite us to listen, to learn, and to marvel at the universe's endless dance of creation. And as long as we keep watching and wondering, their stories will keep unfolding, lighting the way for every curious soul willing to journey among the stars. As we keep floating gently through this cosmic ocean, the universe continues to unfold its wonders before our eyes. The pulsar's steady pulse fades slightly into the background, replaced by the faint, steady glow of distant galaxies and nebulae. But don't drift away just yet. There's still so much to see, so many stories hidden in the light and shadow of space. Let's imagine traveling alongside a newly formed pulsar, fresh from the fiery collapse of a massive star. The star's core has squeezed down into something unimaginably dense, so dense that a single teaspoon would weigh billions of tons. Around us, the remnants of the supernova explosion glow faintly, clouds of gas and dust stretching out in colorful, ghostly shapes. These clouds are the building blocks of new stars and planets, recycled material that will someday birth new life. Our pulsar spins rapidly, sometimes hundreds of times every second. You can almost feel the dizzying speed, like a cosmic lighthouse beacon sweeping its beam across the dark ocean of space. Each pulse you hear is a rhythmic heartbeat of the universe, a signal from a star that refuses to fade quietly. Now, picture the immense magnetic fields wrapped tightly around the pulsar trillions of times, stronger than Earth's magnetic field twisting and turning with its rapid spin. These magnetic fields channel streams of particles, shooting out from the pulsar's poles at nearly the speed of light. Imagine the energy pouring from these jets, powerful enough to light up the space around the pulsar and shape the surrounding nebula into glowing, intricate patterns. Out here, in the quiet vastness, you might notice how even the smallest details tell us so much. The way the pulsar slows down ever so slightly over millions of years gives us clues about its age and the environment it's traveling through. The pulses we detect on Earth are not just signals, they're cosmic postcards, telling us about the conditions in the distant corners of the universe. Let's take a moment to appreciate the contrast between the pulsar and its colossal cousin, the quasar. While the pulsar is a dense, compact powerhouse spinning on its own axis, the quasar is a titanic furnace powered by the gravity of a supermassive black hole, pulling in enormous amounts of gas and dust. This cosmic giant blazes with the combined light of billions of stars, sometimes making entire galaxies look dim in comparison. Imagine the quasar's glowing accretion disk, a swirling maelstrom of matter heated to incredible temperatures as it spirals into the black hole. The energy it releases shapes entire galaxies, creating winds that push out gas and dust, sometimes halting the formation of new stars, and sometimes triggering bursts of stellar birth. This delicate balance shows how violent processes can lead to cosmic creation, how destruction and renewal are intertwined in the universe's grand design. As we observe these marvels, remember that every bit of light and energy traveling toward us has a story to tell. The quasar's brilliant beams come from a time when the universe was less than a quarter of its current age, giving us a glimpse into the cosmic dawn. The pulsar's pulses, though closer, reveal secrets about the physics of matter under extreme conditions that we can't replicate on Earth. So here we are, companions on a journey through space and time, learning from the whispers and roars of stars both old and young. The universe's symphony plays on, a continuous blend of pulses, flashes, and glowing embers, inviting us to listen and wonder without end. Let's dive deeper into the fascinating world of pulsars and quasars, keeping our senses tuned to the subtle rhythms and grand spectacles of the cosmos. A pulsar, though small, holds some of the most extreme physical conditions imaginable. Imagine compressing a mass 1.5 times that of our Sun into a sphere no wider than a city like New York. The matter inside is so dense that a single sugar cube-sized amount would weigh about 1 billion tons on Earth. It's like the universe pressed into a tiny jewel spinning in space. That spin is remarkable. Some pulsars rotate hundreds of times per second, faster than any mechanical device humans have created. This spin is not random. It's a relic of the star's collapse, conserving angular momentum much like a figure skater pulling in their arms to spin faster. Each rotation sweeps powerful magnetic beams across space, like a lighthouse beacon, visible to us as pulses if their beams happen to point our way. Surrounding many pulsars, you might find a nebular glowing cloud of energized particles called a pulsar wind nebula. These clouds shimmer in X-rays and radio waves, shaped by the pulsar's magnetic field and the powerful wind of charged particles it releases. This wind carves and shapes the surrounding space, a delicate dance between fierce energy and cosmic dust. On the other side of the spectrum, quasars are cosmic powerhouses on a scale that boggles the mind. Each quasar's heart is a supermassive black hole, millions to billions of times the mass of our Sun, surrounded by a swirling disk of gas heated to millions of degrees. This disk emits so much energy that it outshines entire galaxies, visible across billions of light years. The jets shooting from quasars are streams of particles moving close to the speed of light, powered by magnetic forces tangled in the spinning disk around the black hole. These jets can extend millions of light years into space, impacting the formation of galaxies and the distribution of matter in the universe. They stir the cosmic soup, sometimes blowing gas away and sometimes compressing it to form new stars. Look around you in this cosmic scene and notice how quasars are most commonly found in the early universe, when galaxies were young and black holes were growing rapidly. The light we see today traveled across vast stretches of space and time, showing us glimpses of the universe as it was billions of years ago. This means when we observe a quasar, we are looking back in time, seeing the universe in its formative years. These ancient beacons illuminate the dark ages of the cosmos, revealing how galaxies and their central black holes grew hand in hand. As you float alongside these marvels, take in the contrast, the compact, precise pulses of neutron stars, born from the death of massive stars, and the sprawling, energetic glow of quasars, powered by the insatiable hunger of black holes. Both extremes tell us about the cycles of creation and destruction that drive the evolution of the cosmos. The universe, in its vastness, is a place where the smallest remnants of stars spin with unfathomable speed, and the largest black holes blaze with the power of billions of suns. Together, they compose a cosmic symphony, a story written in light and gravity, energy and time. In this quiet moment, surrounded by these cosmic wonders, remember that each pulse and flash carries a message. They tell us about forces beyond our everyday experience, about the fate of stars, the growth of galaxies, and the vast history of everything we see and everything we can only imagine. So let's stay with this feeling of wonder, companions floating through the endless night, listening closely to the universe's gentle hum and dazzling bursts, forever invited to explore, understand, and marvel at the grand story unfolding above and around us. The universe has a way of weaving together stories that span unimaginable distances and times, connecting objects as different as pulsars and quasars in ways we're only beginning to understand. Take a moment and picture the aftermath of a massive star's death, a supernova explosion, sending shockwaves rippling through space. At its heart, a pulsar is born, a dense beacon spinning endlessly in the dark, its magnetic field twisting and dancing with fierce energy. This newborn pulsar isn't just a lonely relic. It interacts with its surroundings, blasting out a wind of charged particles that race outward at nearly the speed of light. This pulsar wind creates a glowing nebula, a fragile shell of energized gas shaped by magnetic fields, and the pulsar's relentless spin. In some cases, the pulsar's powerful beams carve cavities in nearby gas clouds, sculpting intricate cosmic sculptures visible across vast distances. While pulsars mark the end of one star's life, quasars tell a different chapter of growth and cosmic hunger. Far away, at the centers of young galaxies, supermassive black holes feast on surrounding gas and dust. This feast creates a swirling, incandescent disk heated to incredible temperatures, radiating energy that can outshine entire galaxies. The light from quasars travels billions of years through space, offering glimpses into the universe's early days when galaxies were rapidly forming and evolving. Imagine those colossal jets streaming out from the poles of a quasar, streaks of matter propelled by magnetic forces at speeds nearing that of light. These jets pierce through the surrounding galactic environment, stirring the cosmic soup and influencing the formation of stars and the distribution of matter over enormous scales. The interplay between the black hole's gravity, the feeding disk, and the jets is a cosmic balancing act, shaping the evolution of entire galaxies. The pulses from a spinning neutron star and the blazing light from a distant quasar are signals from opposite ends of the cosmic scale, yet both speak volumes about the forces that govern our universe. Pulsars, despite their tiny size, help astronomers test the laws of physics under extreme conditions and even detect ripples in spacetime called gravitational waves. Quasars, meanwhile, serve as cosmic lighthouses, illuminating the large-scale structure of the cosmos and helping us trace the history of galaxy formation. Together, these phenomena remind us that the universe is a dynamic place, constantly changing, cycling through birth and death, destruction and creation. They invite us to imagine a cosmos where time stretches across billions of years, where tiny pulses and mighty beams carry stories from the farthest reaches to our own quiet corner of space. Let your mind rest in that vastness, feeling the connection to the ancient light and the spinning stars, and carrying with you a sense of wonder that these distant objects, separated by unimaginable distances, are part of the same grand cosmic dance we are privileged to witness. Let's keep floating in this vast, quiet ocean of space, where every pulse and flash tells a story older than time itself. Imagine standing right beside that newborn pulsar again, feeling the faint, ghostly glow of its pulsar wind nebula spreading out like a shimmering veil. The charged particles racing away from the pulsar carry with them energy and secrets, whispers of magnetic fields twisting, of gravity warping space itself. You might notice how the pulsar's spin slows imperceptibly over thousands and millions of years, a cosmic clock ticking ever so slightly slower. This gradual slowdown isn't just a sign of a gates, it's a clue about what's happening deep inside that dense core, where matter is squeezed to extremes no laboratory on Earth can mimic. It's a natural experiment running out there in the void, waiting for us to decode its messages. As we drift further, picture the vast distances that separate us from the quasars blazing billions of light years away. These ancient giants shine like cosmic lanterns, their brilliant light stretching and reddening as it journeys toward us through expanding space. Each photon arriving now started its journey long before Earth even existed, carrying stories from an epoch when the universe was young and chaotic, galaxies colliding and growing rapidly. Look closer at those jets streaming out from quasars, spewing particles at nearly light speed, extending millions of light years into the surrounding cosmos. These jets are not just dazzling displays, they reshape their host galaxies, pushing away gas that might otherwise form new stars or compressing clouds to trigger fresh bursts of starbirth. It's a wild cosmic feedback loop, where destruction and creation dance hand in hand. Notice how pulsars and quasars, though wildly different, both reveal the fundamental forces shaping the cosmos: gravity's relentless pull, magnetism's invisible grasp, and energy's transformative power. Pulsars are the remnants of death, spinning embers glowing with magnetic fire, while quasars are the blazing hearts of youthful galaxies, hungry and vibrant. Between them, the universe tells a story of cycle stars born, stars dying, galaxies growing, and black holes feeding. This endless rhythm has been playing out for billions of years, and we, here on this small blue planet, get to be part of the story by simply looking up and listening. So as we float here together, wrapped in the hush of space, remember these distant beacons. The next time you gaze up at the night sky, imagine the pulses from neutron stars beating in time somewhere far away, and the radiant glow of quasars shining from the dawn of time. They remind us that the universe is alive, full of mystery and wonder, and that we are, in our own quiet way, connected to its vast, unfolding tale. The universe has a way of weaving together stories that span unimaginable distances and times, connecting objects as different as pulsars and quasars in ways we're only beginning to understand. Take a moment and picture the aftermath of a massive star's death, a supernova explosion, sending shockwaves rippling through space. At its heart, a pulsar is born, a dense beacon spinning endlessly in the dark, its magnetic field twisting and dancing with fierce energy. This newborn pulsar isn't just a lonely relic. It interacts with its surroundings, blasting out a wind of charged particles that race outward at nearly the speed of light. This pulsar wind creates a glowing nebula, a fragile shell of energized gas shaped by magnetic fields, and the pulsar's relentless spin. In some cases, the pulsar's powerful beams carve cavities in nearby gas clouds, sculpting intricate cosmic sculptures, visible across vast distances. While pulsars mark the end of one star's life, quasars tell a different chapter of growth and cosmic hunger. Far away, at the centers of young galaxies, supermassive black holes feast on surrounding gas and dust. This feast creates a swirling, incandescent disk heated to incredible temperatures, radiating energy that can outshine entire galaxies. The light from quasars travels billions of years through space, offering glimpses into the universe's early days when galaxies were rapidly forming and evolving. Imagine those colossal jets streaming out from the poles of a quasar, streaks of matter propelled by magnetic forces at speeds nearing that of light. These jets pierce through the surrounding galactic environment, stirring the cosmic soup and influencing the formation of stars and the distribution of matter over enormous scales. The interplay between the black hole's gravity, the feeding disk, and the jets is a cosmic balancing act, shaping the evolution of entire galaxies. The pulses from a spinning neutron star and the blazing light from a distant quasar are signals from opposite ends of the cosmic scale, yet both speak volumes about the forces that govern our universe. Pulsars, despite their tiny size, help astronomers test the laws of physics under extreme conditions and even detect ripples in space-time called gravitational waves. Quasars, meanwhile, serve as cosmic lighthouses, illuminating the large-scale structure of the cosmos and helping us trace the history of galaxy formation. Together, these phenomena remind us that the universe is a dynamic place, constantly changing, cycling through birth and death, destruction and creation. They invite us to imagine a cosmos where time stretches across billions of years, where tiny pulses and mighty beams carry stories from the farthest reaches to our own quiet corner of space. Let your mind rest in that vastness, feeling the connection to the ancient light and the spinning stars, and carrying with you a sense of wonder that these distant objects, separated by unimaginable distances, are part of the same grand cosmic dance we are privileged to witness. Now, as we continue to drift through this cosmic ocean, it's worth pondering the sheer scale of what we're contemplating. A pulsar might be only about 20 kilometers across, roughly the size of a small city, but within it lies more mass than our sun packed into that tiny sphere. It spins so fast that some complete hundreds of rotations each second. Imagine a spinning top, but one made of nuclear matter, vibrating with magnetic energy so intense that it would tear apart anything close by. You can almost feel the pulse if you let your imagination stretch far enough. That rhythmic beat, steady and unwavering, is like a heartbeat for this remnant of a long-gone star. Each pulse travels across the vast emptiness, a lighthouse beam sweeping through the cosmic dark, a beacon signaling a presence that has endured for millions of years. In contrast, a quasar's light is a roaring blaze from the depths of space. These giants are fueled by black holes millions or even billions of times more massive than our sun. As they devour matter, the swirling disk around the black hole heats to incredible temperatures, lighting up with the energy of countless suns combined. This radiant energy jets out in narrow beams, sometimes shooting for millions of light years, creating spectacular cosmic fireworks visible across the universe. Picture a galaxy in its infancy, chaotic and full of gas and dust, with a black hole at its center feeding on this cosmic buffet. The quasar shines so brightly it outshines the entire galaxy that hosts it, making it visible billions of light years away. We see quasars not just as distant points of light, but as time capsules, glimpses into the early universe when galaxies were forming, colliding, and evolving rapidly. Both pulsars and quasars tell stories about the invisible forces shaping everything we see. Pulsars reveal the extremes of matter and magnetic fields, while quasars illuminate the violent processes that shaped galaxies and the cosmic web. Both help us understand gravity, magnetism, and energy on scales that boggle the mind. And so, as we float alongside these cosmic lighthouses and beacons, take a moment to breathe in the quiet majesty of the universe. Feel the pulse of distant neutron stars, and glimpse the radiant fury of quasars blazing from the dawn of time. These celestial storytellers whisper of beginnings and ends, of creation and destruction, and invite us to join the endless dance of the cosmos. Let's keep drifting deeper into this vast expanse where time and space stretch beyond our daily understanding. Imagine the pulsar again, this spinning beacon born from a star's violent death. Each rotation sends out waves of energy, sometimes visible as pulses of light, sometimes as radio waves that astronomers pick up with their giant dishes on Earth. The regularity is almost hypnotic, like the steady tick of a cosmic clock keeping time in a universe that often feels chaotic. Reach out with your mind and feel the weight of that pulsar's gravity. It's crushingly intense, squeezing matter so tightly that atoms are crushed flat, electrons merging with protons to form neutrons in a dense sea. It's matter in a state that simply doesn't exist anywhere on Earth. And yet, here it is, spinning and glowing far across space, a relic of cataclysmic change. While pulsars stand as remnants, quasars are more like blazing lighthouses guiding us to the early universe's secrets. Their brightness can be mind-boggling sometimes, shining with the power of 1,000 trillion suns. And that light has traveled for billions of years to reach us, telling stories of a universe that was young and wildly energetic. Feel the tug of those jets shooting out from the quasar's core. They slice through space at incredible speeds, pushing and shaping the gas and dust around them. These jets don't just blaze a trail, they influence how galaxies grow and evolve. It's a cosmic feedback loop where black holes help sculpt their own homes. Now, imagine you're floating near one of these jets, feeling the sheer force as it punches through the galactic environment. The particles streaming out are energized by magnetic fields stronger than any we can recreate here, whipping around at near light speed. That energy stirs the cosmic material, triggering bursts of star formation or sometimes blowing gas away, halting the growth of the galaxy. Between pulsars and quasars, we have two extremes of cosmic activity, the remnants of explosive death and the radiant hunger of a supermassive black hole. They're chapters in the universe's grand story about how matter and energy behave on scales both tiny and enormous. And here we are, companions on this quiet voyage through the dark. The universe offers us its light and pulses, whispers of processes that have shaped everything we know, from the atoms in our bodies to the vast clusters of galaxies. So breathe in the calm vastness. Let the steady pulse of a distant neutron star soothe your thoughts. Let the fierce glow of a quasar remind you how dynamic and alive the cosmos really is. We're connected, you and I, by these cosmic lighthouses, by their ancient light and rhythmic signals. They carry stories through space and time, inviting us to listen closely, to wonder deeply, and to feel our place within the great unfolding of the universe. As we begin to gently pull away from the dazzling light of quasars and the rhythmic pulses of spinning neutron stars, take a moment to feel the stillness of this vast universe stretching around us. The silence here is not empty, it's filled with stories, with echoes of ancient explosions and the quiet birth of new light. In that quiet, there is a kind of peace, a reminder that everything, no matter how fierce or bright, eventually fades, changes, and becomes part of something new. Consider the journey of a pulsar, a tiny city-sized sphere, born in the fire of a dying star's last breath, spinning faster than a hummingbird's wings, sending out steady pulses like a cosmic metronome. Each pulse is a whisper from the past, a signal that has traveled millions, sometimes billions, of years to reach us. These pulses are messages encoded in light and radio waves, telling us about the extreme physics of matter crushed beyond our imagination, magnetic fields twisting and snapping in wild patterns, and gravity so intense it bends space and time itself. Farther away, the quasar shines with a different kind of brilliance. It's a cosmic furnace where black holes millions or billions of times the sun's mass consume gas and dust, creating a whirlpool of light and energy so powerful it outshines entire galaxies. These radiant beacons remind us how even the darkest objects in the universe can blaze with light, shaping the galaxies around them and influencing the grand architecture of the cosmos. They are time machines, showing us the universe as it was billions of years ago, when everything was younger, louder, and more energetic. Together, pulsars and quasars invite us to marvel at extremesat, the smallest and densest stars that pulse like cosmic lighthouses, and at the largest, most voracious black holes lighting up the early universe. Their stories are threads woven into the vast tapestry of space and time, connecting us to the cosmos in ways that stretch beyond what we can see or even fully understand. And yet, despite their immense power and distance, these celestial wonders speak to something deeply human: our endless curiosity, our desire to explore, and our awe for the unknown. They remind us that we are part of a universe that is not silent or still, but alive with motion, light, and endless stories waiting to be discovered. So as we slowly drift away from these cosmic lighthouses, carry with you the pulse of the neutron star, steady and eternal. Hold the glow of the quasar close, a blazing reminder of creation and destruction dancing hand in hand. Let their stories inspire a quiet wonder, a gentle reminder that no matter where we are in space or time, we are connected to this vast and beautiful universe. Thank you for sharing this journey with me. Wherever you are right now, I hope you feel a little closer to the stars, a little more part of this endless cosmic dance. Until we meet again among the stars, keep looking up, keep wondering, and keep feeling the quiet magic of the universe around you.